Hi everyone, my name is Isaac Berry from Berry Science Lab, and welcome back to Quantum Mechanics. Today, we're going to be talking about angular momentum. That's right, not the classical version. But we actually will talk about the classical version a little bit in order to get some insight on what the quantum version will act like. So first of all, what is angular momentum? Well, hopefully you already know that. When we have a rotating object, just like the linear momentum we attribute to its tangential velocity, there's also an angular momentum associated with its angular velocity, the speed at which it's moving. And of course, torque acts like the change in momentum over time. So, of course, if torque is equal to 0, then that means momentum is conserved. So, what is angular momentum? Well, you probably remember it as either one of these two formulas. But this only goes for a circular or elliptical orbit. In general, what happens if we release an object into 3D? In this case, an object can rotate and wiggle and wobble around in any way it wants to, which means it can also constantly change its plane of rotation. That means that two objects with totally different trajectories can have the exact same angular momentum, acceleration, and velocity all at the same time, as long as they're in two different planes of rotation. Hence, I propose to attribute the normal vector to the plane of rotation as a direction to L. But not just that, L changes when you have things like this. Whenever R and P aren't perfectly perpendicular, which they aren't always, even though they're perpendicular situations like a circular or elliptical orbit, if R and P are not exactly perpendicular, and they're not perpendicular in an elliptical orbit either, sorry, this should become sine theta. That's right, we are going to write L as mv cross R. Or more succinctly, we can use the associative property and write it as P cross R. Where's the eraser? So there we go. P cross R. How does this relate to quantum mechanics? Well, first of all, why is it important? Hydrogen atom. Next question. Where do we define angular momentum? Well, it all starts with defining position, which is the position operator as we all know, and the momentum operator, which is defined in terms of position as minus I h bar partial x. And yes, it makes sense that there's nothing associated with the partial x, since this is, after all, an operator. It needs to be multiplied by a wave function or some other function to make any kind of sense. So in that way, L is just P cross R, right? Simple. P cross R. Well, oh wait. This actually doesn't work, right? Because P here is a vector with three different components. How do you substitute what's still sort of a scalar operator into this? Well, good question. We break L up into its three components, which have to be separate operators. P here is just a one-dimensional momentum operator. The three-dimensional momentum operator is sort of a vector of operators. You just have Px is minus I h bar partial x. Py is this but with a y. Pz is just this but with a z. It all makes sense. So now in classical mechanics, taking this cross product means, well, I haven't actually memorized the cross product, so I'm going to use the determinant trick. Basically, you take this, the components are Px, Py, Pz, and x, y, z, and you take the determinant of this matrix as far as it is a matrix, even though these are definitely not scalars. So we get zpy minus x, wait, no, ipyz, hold up, oh wait, no, I'm blind, minus pzy, that's the first component. Then the second component is going to be xpz minus zpx. And the last component should be, oh, you want me to use the whiteboard? No. Okay. Alright, you're just cleaning. xpy minus ypx. So, here we go. These are the components. Now, let's see what happens when we plug in the definition of the momentum operator. So this is Lx, Ly, Lz. So what happens when we plug in their definitions? Well, we get Lx is going to be z, py is going to be, let's factor out the minus ih bar in preparation. So this is going to be z partial y minus y partial z. Ly is going to be minus ih bar times x partial z minus z partial x. They try to bring me down, way down, way down. I always knew that one day. Okay, here we go. So these are the three components we're working with. Now, second question. Recall that the uncertainty principle told us that the accuracy with which you can measure two related variables depends on their commutator. Well, the commutator of their associated operators. So, in the case of position and momentum, because of the way their operators are structured, the standard deviations have to be greater than h bar over 2. Now we call two operators with a zero commutator compatible, because then the product of their standard deviations is greater than or equal to 0. And that means we can measure them with arbitrary accuracy and find eigenstates that satisfy both of them perfectly at once. So, first, let's do the natural check. Are these three compatible with one another? Or rather, is Lx compatible with Ly, Ly compatible with Lz, and Lz compatible with Lx? Well, to figure it out, we're going to have to calculate the commutator of Lx and Ly, and then, because of the way these are structured, do the rest by cyclic permutation. Yeah. Don't erase these definitions. So, what's the commutator going to look like? Well, we don't get much information by just writing Lx Ly minus Ly Lx. We actually have to work on it using a test function in order to know what it is. So, that's what was distracting me. So we get the commutator of Lx Ly F is going to be equal to, well, Lx minus, which is equal to, well, this first term is going to be, first let's factor out ih bar squared, or minus ih bar squared. And I cubed squared is I to the sixth, which is minus 1. So this is minus h bar squared multiplied by, well, Lx is z partial y, Ly is x partial zf minus z partial xf minus y partial z, the same exact thing. And then minus Ly Lxf is going to be minus, well, Ly is going to be x partial z times z partial yf minus y partial zf plus z partial x of z partial yf minus y partial zf. Here we go. So this is the commutator applied to some test function f. Now we have to get to simplifying it because this also tells us nothing. So this will give us what? Minus h bar squared multiplied by, well, this is going to be a hell of a lot of using the chain rule. We get from the first term z partial y of all of this. So we get z, well, this requires the product rule. Partial y of x is 0, so we don't consider that term. Partial y partial zf. I'm going to write that as fyz minus partial y z partial xf. So partial y of z is 0. We only consider partial y partial xf, which is minus z fxy. Then you have minus y partial z of this, which is going to be term by term. We're just going to have x partial z squared. I'm writing it as fzz, or f partial derivative of this, that, because that makes things a lot quicker. Minus z, oh wait, the product rule terms are actually non-zero on this one. So we get minus partial xf minus z f, oh, so this becomes fx xz. Alright, and now we have over here minus x. Oh, and recall fxz is equal to fzx. The order of derivatives doesn't matter for continuous functions. So minus x partial z of this, so that's going to be minus x times partial yf, which is fy, plus z fyz minus y partial zzf, which is yfzz. And then we have plus z partial x. Both of the product rule terms here are going to go to 0. So we just get zfxy minus yfxz. And things actually overwhelmingly simplify from here. Why? Well, just let's try to look for a refactorization of these. First, let's gather up all the fyz terms we can find, since it's the first in the sequence. Well, we can find an xz term, obviously, since the z distributes to the x. fyz. Oh, I can find another one here. Minus x times z. Oh wow, that goes to 0. Maybe that's just a funky coincidence. Alright, then next up we have fxy. So let's also add all of the terms containing it. Well, we have minus z squared off the bat. xy. Oh, and we have plus z squared there. I'm starting to see a pattern here. Then we have fzz. Well, we have a minus xy here. And anything else? Oh, there's a minus x times minus y, which is plus xy here. That also cancels out. I think my suspicions are confirmed. Then we have, well, what else is there? Fx terms. So plus fx times y. Well, I can't find another term, so this doesn't cancel out. Weird. Then we have, well, xz. So we have plus fxz minus y times minus z is yz. And then fxz z times minus y, so that's minus zy. that is also 0. And then, well, let's see, I find an fy over here. So that's just, well, there's no other fy terms, so I guess it's just plus fy times minus x. And everything else we've already covered. Fyz over there. Fxy over there. Fzz over there. Fxz over there. Which means that these two are the only ones left. So we get minus h bar squared multiplied by yfx minus xfy. Wait a moment. That's minus h bar squared times y partial xf minus x partial yf. And so, in the end, Lx, Ly, remember we were multiplying by a test function, so if we remove the test function, it's just h bar squared multiplied by x partial y minus y partial x. Wait a minute, that looks eerily similar to what Lz looks like. In fact, if we factorize this, this is just going to be h bar multiplied by h bar. Then this is going to be IH bar times minus IH bar. This is just LZ. And so we simplify everything to IH bar LZ for the commutator of LX and LY. And by cyclic permutation, the commutator of LY and LZ becomes IH bar LX, and the commutator of LZ LX becomes IH bar LY. And you can get the commutator for whenever we reverse the order by just flipping the sign. If the commutators are non-zero most of the time, that means that unless one of these components is 0, the other two are not compatible. So, in fact, there's an uncertainty stemming from them that's the exact same as the uncertainty between x and p, the momentum. So what is compatible? Because now we know that we can never get a concrete direction for the angular momentum. None of the three components can be compatible at the same time, unless one of the components is 0, of course. So, how can we figure out things that are compatible? Well, let's try something random, like the magnitude of the angular momentum. Except that contains a nasty square root, and square roots are bad for taking derivatives. So how about we make it squared? So that becomes, let's take it with Lx because that's the first component. What does this give us? Lx squared, Lx, plus Ly squared, Lx, plus Lz squared, Lx. There's no secret that this is just 0 since it's Lx cubed minus Lx cubed. And these two simplify using the commutator formula into Ly, Lx, plus, Ly, Lx, Ly, and then plus Lz, Lx, plus Lz, Lx, Lz. But wait a moment. Ly, Lx's commutator is just minus IH bar Lz. And same thing applies here. These actually commute. Meanwhile, Lz, Lx's commutator is IH bar Ly. So these two cancel. And these two cancel. Would you look at that? It's a miracle. And of course, by cyclic permutation, that means that the norm squared of L is compatible with all three of its components. Which means that we can both know the magnitude of the angular momentum and one of its components at any given time. If the third component happens to be zero, and this also gives some intuition on why, if the third component is zero, we happen to exactly know the second component. Since if we can know both the magnitude and the first component at the same time, if we know that the third component is zero, obviously we know the second component by just, process of elimination, not process of elimination, substitution. So that means that we can find simultaneous eigenstates for, well, we can't find them for two components at once, but we can find them for some component of angular momentum and the magnitude at once. Now, doing that will be left to another lecture, but we'll use something similar to the ladder operator technique we used a very long time ago dealing with the time-independent Schrodinger equation.